Good morning, good afternoon, everyone, and welcome. I'm Barry Hopton, Head of Wastewater at Xylem UK, and thank you for joining us. I'm just going to give it another 10 to 15 seconds just to let the room fill up. So just bear with us for, I say, another 10 to 15 seconds, just while we let the remaining few people join. Okay, all right. I think that's everyone at this point. So again, thank you for joining. Really excited about today's session. This session today aims to bring together industry experts to explore how the sector can take indirect potable reuse from concept to full-scale operational reality. At Xylem, our treatment technologies and operational insights are already supporting major IPR, indirect potable reuse plants, worldwide. So hopefully this session today provides some valuable insights for everyone attending. The structure of today's session will be as follows. The first half, for around 30 minutes, will run through the presentations from our experts and guest speakers today. The second half will then comprise of our questions presented to our guest and our expert speakers. We will be running a poll today. So hopefully this works, and we would love your feedback and insight during the session on these polls. And again, throughout today's session, please use the chat box to answer and submit your questions. Just a little bit of housekeeping. We're currently in listen-only mode, and we're recording this session so it can be used later. Thank you. Next slide, Uwe. So I'm really excited to introduce the team we have with us today. The presenters are Dr. Uwe Uberner. Uwe is a senior process engineer at Xylem Water Solutions, responsible for treatment solutions in water reuse and advanced oxidation. He holds a master's and a PhD in environmental engineering from the University of Berlin, and also has published more than 70 peer-reviewed articles in the field of advanced water treatment and reuse. Welcome. And secondly, our guest speaker today, Hermano Salazar Benitez, is a water reuse engineer at Hampton Road Sanitation District Sustainable Water Initiative for Tomorrow, aptly known as SWIFT. For those who don't know, that's in the state of Virginia. Hermano is the chair of the Water Reuse Program Committee and the second vice chair of the Water Reuse Community at the Water Environment Federation. Today, our guest speaker and our expert will be discussing the main points around designing for continuous protection of public health, monitoring of contaminants that cannot be measured in real time, and using critical control point-based frameworks to underpin compliance and confidence. Just a reminder, once again, please get involved in any of the polls and questions you see today. We'd really love your engagement. For those who can't stay for the full duration, we will be sending out a recording via link after the session for you to be able to recap and share. Before we get started, let's jump into our first poll. Okay, please can you fill out one of the options below? What stage is your current organization currently at with IPR? Okay, fantastic. Fantastic. Okay, so some really interesting results here. Quite an even keel, but we've got predominantly early stage strategy for feasibility or pilot demonstration. Fantastic. I think given the UK's position and where we are, that aligns really well with the market. So thank you for that intel. That's really good to hear. Okay, next we'll dive into our presentations from Dr. Uwe Ubener and Hermano. Thank you very much.
Thank you, Barry, for the introduction. So I will just give a brief introduction into the topic of potable reuse, and then introduce a little bit how we can control and especially monitor the treatment processes, so that we really continuously demonstrate that they're doing what they're supposed to do. Yeah, let's directly start into it. If my presentation working, yeah. So just a few words about terminology. So regarding potable reuse, we have two different options. We have indirect potable reuse. That means we're providing advanced treatment, and then we're going into an environmental buffer. That can be an aquifer, and as you see here in the first picture, or it can be also surface water. So in UK, there are a lot of discussions going into reservoirs or into rivers that are upstream of drinking water treatment plants. The alternative option would be direct potable reuse, and that is where we would go directly after the advanced treatment, either in the drinking water treatment facility or even directly into the distribution system. So typically a part stream. And the bigger challenge here is the main challenge, of course, that we don't have any response time anymore to really respond to failures and problems in direct potable reuse. Okay, when it comes to potable reuse, of course, we need to make sure that we completely mitigate any health risk related to contaminants from the wastewater. And there are different frameworks how advanced treatment can be described. I like this from a presentation from the people from Trusted Technology a while ago. They call it the 4 R's. So the advanced treatment needs to be redundant. That means, first of all, we need to have redundant treatment regarding if a treatment is failing, that we still can supply the water. But it also means that especially for pathogens, we need redundant processes. So we don't want to rely on only one disinfection barrier, for example. The treatment needs to be robust, which especially refers to we want to have different types of barriers so that we can really address and control all different types of contaminants, especially chemicals. Of course, treatment needs to be reliable. So we're talking about potable reuse, acute health risk. So 24/7 treatment, and it all needs to work, of course, all the time. And the treatment train needs to be resilient to adapt, to respond to failures. Okay, so with that said, there are a lot of different options how you can design a treatment train. In the recent past, there are two major concepts, I would say, that are dominating. And one is the RO-based concept. That's often to also refer to fully advanced treatment or the golden standard of California. So it's a membrane filtration followed by reverse osmosis, and then we have a final UV advanced oxidation step. Alternative concepts are often referred to carbon-based advanced treatment. We will hear more about this also from Hermano today after my presentation. The major barrier is here ozone, followed by a biological activated filtration, and then a GAC. This is often combined with additional treatment like UV disinfection or alternative barriers for some specific chemicals that are occurring. So the carbon-based advanced treatment has the advantage that it comes at a lower operational costs. And especially when we're talking about inland facilities, we don't have the brine, the concentrate produced from RO, which is a real management and treatment issue. But of course, apart from the better treatment, the more advanced treatment with the RO-based, we also have other potential advantages. regarding the byproduct formation, which may be an issue with ozone, especially when we have high bromide levels. And of course, also, we often have higher salinity in our treated wastewater that we might even need a step to reduce the salinity. Okay, so with that, let's look into the treatment targets. So in Europe, I often notice a lot of discussion regarding chemicals. When we look at existing frameworks, then they are mostly driven by pathogen removal, because that's driving the acute risk to human health. And I just have here three different frameworks that I want to very quickly show. The WHO published potable reuse guidelines. I think that was in 2017. That's a very nice document, by the way. I recommend reading it. So they all frameworks do the same. So they specify what's this potential maximum concentration we have in our raw sewage, and then they identify what is the maximum risk level we want to achieve in the reclaimed water, and based on this, they define log removal values that need to be achieved by the entire treatment. So WHO, you see, we have them for virus, bacteria, protozoa. In California, they don't specify bacteria because they assume if virus is removed, bacteria is always removed better. But they specify two different types of protozoa, Giardia and Cryptosporidium. So the indirect potable reuse is always referred to this 12-10-10 rule that you need to achieve. And when it's going to direct potable reuse, they even expect higher values. That's also from California, more recent regulation, going into 20 for viruses, 14 for Giardia, and 15 for Cryptosporidium. How do we come to these high numbers? The approach is that we're just summing up the treatment, the removal credits given to every individual processes. So you can see here, you have the different steps for the example of direct potable reuse, like 6 for ozone, 2 for RO, 6 for UV AUP, and then chlorine. And then we can sum them up and see if we achieve the target. The problem here is, for us, how do we confirm this, and how do we continuously demonstrate that we achieve these targets? And that's why you see sometimes a little bit surprising numbers. When we're looking here into reverse osmosis, we're aware that this is mainly disinfecting completely, but we only give 2 credits for disinfection for reverse osmosis. And this is simply because we cannot monitor the pathogens continuously, and we don't have a good measure for RO right now to demonstrate that there are no failures. So for RO, we typically can measure conductivity. There are also other parameters nowadays, but this, if conductivity is increasing or not increasing, it's only accounting for 2 log. And not for 6 log. Okay, so how do we do this demonstration continuously? And there are two major options. One is that we monitor operational parameters. The easiest approach is for chemical disinfection, the CT value. So we're monitoring the disinfectant at the reactor outlet, multiplying it by the contact time. And then we know, and this is correlating to removal of specific pathogens. And the other alternative is using surrogates. And the surrogate parameter would be a parameter that is removed by the process, and that is a parameter that we can continuously measure to confirm the removal. Okay, I'm gonna go into 2 examples right now. Since I'm working for Vedico Xylem, I'm focusing on UV-based and ozone-based treatment. So for for UV disinfection and also UV AUP, we're using validated reactors. What does it mean? So we're doing a lot of testing at different conditions, and this testing will give us a reactor equation that describes the removal, the log removal value at every specific condition. So you see here UV absorbance, that's the UV intensity. We can measure proximity to the lamp, and this is the flow rate, and this is the sensitivity of the specific microbe. So that's describing this, and then when we operate the system, we can then monitor exactly those parameters. You have here flow rate, UV transmittance, UV intensity, and use that to really confirm that we all the time have the correct UV dose applied. When we now want to do UV AUP, we can add additional critical control points for the performance of the oxidation. This would be, for example, correlated to the free chlorine in the reactor inlet. Sometimes we're also measuring residual free chlorine at the outlet for UV chlorine process as an example. Okay, let's briefly go into ozonation and ozone-based oxidation. I already mentioned the CT concept. So that's the standard approach to confirm ozonation works well. So we're measuring dissolved ozone in the outlet, and we're multiplying this or integrating it over time. That would be the ozone exposure, or multiplying it with the time. That's a more conservative approach. So that's the standard for drinking water treatment, and this is correlating then with the inactivation of pathogens. However, when we look at the ozone decay in wastewater or in potable reuse applications, we often see this. So already within the first 20 seconds, the majority of the ozone has been removed, and often not much more ozone is needed for the treatment. And when we go for ozone peroxide, this would be even more extreme. So we don't see any residue, so we cannot measure the residue. So what are we doing then? And the approach here is to go to use surrogates to confirm the disinfection. So an ideal surrogate would be simple to analyze with online instrumentation, would indicate the performance of a UV treatment process. And ideally, we have a direct correlation with the surrogate and the target contaminant. So I have here a picture of 3 potential surrogates. You see the DOC, all of them, the UV absorbance and the color measured at 436 nanometers. And you see all of them are, of course, easy to analyze. But DOC, for example, it doesn't show a removal during ozonation, so it's not a good surrogate for this process. The UV, the color actually is often removed too fast, but the UV absorbance based on this second criteria would be a good candidate as a surrogate. And here, this is my last figure for today, showing you a result from a study also done at Virginia Tech in collaboration, I think, with the team from Germano. So you see the log10 removal, the LRV for viruses correlated to the change of UV absorbance. And you see there's a quite good correlation between that. So that means you can operate the reactor by at a constant change of UV absorbance, and then you would be able to confirm that you achieve a minimum log reduction within this process. This is a concept that has been discussed and proposed. As far as I know, that's not implemented anywhere. But similar concepts are also right now discussed for use of reverse osmosis, for example. Yeah, with that, I want to stop here. And Barry, I don't know if you're jumping in or if I directly hand over to Germano for the second part.
Directly over to Germano, please.
Okay, Germano, so I hand over the word to you.
All right, thank you. Exciting to be here today. Thank you for joining. Good afternoon, everybody. It's good morning for me, but again, excited to be here with you today. Uwe, you can go to the next slide. All right, so I'm just going to jump into it. So Hampton Road Sanitation District, it is a wastewater utility, and we have been in operation since 1940. We serve to a population of about 2 million of Virginians, and we have a design capacity to treat about 850 megaliters per day, but on a daily basis, we treat about 570 megaliters per day. We have 8 major wastewater treatment plants, and the idea is to build Swift only on some of them, which I'm going to indicate which ones later on. You can go to the next slide. Okay, so this is the current state of wastewater treatment in our region in Hampton Roads. So there are a combination of drinking water plants that take about 80% of the surface water, take about 20% of the groundwater. They treat it, they make it potable. Then that water goes to the different houses and businesses. Once the water is used, then that's the water that we receive in our facilities on the wastewater side. But the idea now is to collect secondary effluent from the wastewater facility and to put it through SWIFT, which is an advanced water treatment technology, to implement indirect potable reuse. So the idea here, as you can see in this graph, is to put the water back into the ground, into the aquifer. By doing this, of course, we're going to be helping with different goals. One of them is to reduce the rate of land subsidence and protect the water from saltwater intrusion. We live on the coast, so there is a potential for the seawater to get into the Potomac aquifer, which we don't want. Also, we're going to provide a regulatory stability for the wastewater side. So every 5 years or so, we get new permits, and we need to be able to meet those permits. So right now, the dynamic is that we do research, we try to find the technology that we want to be able to meet permit, and then we implement it, and then we meet permit. And then again, we need to do research again, trying to do again the same. But the idea of SWIFT basically is to plan to go all the way to drinking water standards. So then, I guess the regulators, can't ask for anything better than that. So that's the whole idea. And of course, by implementing SWIFT, we're going to be supporting our economy here in Virginia. Next slide. All right, so like I mentioned before, so right now from the 8 major wastewater treatment plants, the plan is to implement SWIFT on 3 of them. So by 2030, which is only 4 years from now, we should be able to have 190 megaliters per day in using SWIFT as the main technology. Next. Okay, so the talk today is going to mainly focus on our proposed regulatory limits and how we meet them. How we monitor and how do we make sure that we're meeting these limits before putting the water into the ground. So in regards to MCLs, the maximum contaminant levels, we have to meet all of them to be able to consider our water potable. We have a limit of 5 milliliters per liter for total nitrogen. In regards of turbidity, it's very similar to drinking water standards. It is based on how much credits you want for LRVs, which I'm going to explain this later, a little bit better later. In regards of TOC, our limit is 4 milliliters per liter, which in comparison with California, this is higher. In California, they have a limit of 0.5 milliliters per liter, but basically that's dictating what technology you should use. So in California, if you're going to implement reuse and have a limit of 0.5, you have to use membranes. If not, it's not really feasible to use carbon to meet those limits. But in our case, we're proposing to have a TOC limit of 4 milliliters per liter. For total coliform, which is the bacteria, we're proposing is very similar to drinking water standards, like less than 2 CFU per 100 mils. And also in regards of LRVs, we're proposing to achieve the 12-10-10 rule for virus virus, crypto, and giardia. And I'm going to explain later how we achieve this throughout the carbon-based strain. E. coli also has to be non-detect. And in regards of unregulated chemicals, we're not proposing anything specifically, but of course we're monitoring a suite of different chemicals or contaminants. And a good example of this is PFAS and 1,4-dioxanes that we also monitor. And in regards of TDS, the total dissolved solids, we're not proposing anything. And again, this one is specifically because we want to make sure that the water that we produce is compatible with the aquifer, which is already high in TDS. You can go to the next one. Okay, so this is our process flow diagram. I'm not going to explain this too much in details. I have a summary at the very end so we can understand better what's happening on each train. But basically, we collect secondary effluent, goes to the first step, which is rapid mix flocculation sedimentation. Here we add two chemicals. One is aluminum chlorohydrate and polymer. And then we treat the water. Then the next step is ozonation. Here of course, we add ozone, and we also add monochloramine, and this is specifically to control bromate formation. After ozonation, we add phosphoric acid, and this is because sometimes the wastewater side, they do a great job in removing phosphorus, and we just want to make sure that we do not limit that nutrient going into the biofilter. So we just add a little bit of it. And then because we add monochloramine to control bromine formation, we add sodium bisulfite just to quench that remaining chlorine. And here we're feeding propane gas, and this is specifically to treat 1,4-dioxane biologically. I think we're one of the first, water reuse projects that are implementing propane gas into the water. I'm not going to focus on this, but if you have any question on this, you can follow up after the talk. And then we have biofiltration, which is basically we have 1 foot of gravel, 1 foot of sand, and then 5 feet of carbon media on top. We do not replace this media. It's a place just for the biomass to live in. After biofiltration, then the water goes to a GAC pump station. This is the water that we can use to backwash any biofilter or to go to the next step, which is GAC. Here is where we control our TOC limit of 4 milliliters per liter. And then after that, the water goes to the UV reactor, and this is mainly to achieve our LRV credits, which I'm going to explain later again how we do it. And then after UV, we adjust the pH using sodium hydroxide, and then we add a little bit of sodium hypochlorite just to make sure that we have a little bit of chlorine residual, and this is to avoid any bio falling on the screens at the well. By the way, this well is very deep, so it's like 1,500 feet below ground. You can go to the next one. All right, so again, the main focus here is to show or demonstrate how we make sure the water is always safe. So our point of compliance is right before the water goes into the well. And we have like different automation controls that will make sure that the water doesn't meet or doesn't go into the aquifer if we're not meeting our regulatory limits. So here, I'm going to explain that we have mainly 3 diversion points. And Uwe, you can go to the next one. So the first diversion point is between ozonation and biofiltration. Basically here, we just bypass biofiltration. We just treat the water all the way to ozonation. And this is, for example, if we believe that bromate is higher, we will bypass, biofiltration. Or if we lose the ozone feed for any reason, we will bypass biofiltration. This is one of them. The second one, and you can go to the next slide. Yeah, the second one is after biofiltration. So basically, we put biofilter in waste, and then nothing else is being treated. Probably this is the most common one that we see. And again, this one is because we want, if we have any upsets on the wastewater side, or we're not able to meet, our regulatory limits, our desire is to always, at least to put biofilters always in filter to waste. Just because, again, in biofilters we have biomass, we have bacteria in there that we just want to make sure that they are always happy and they have enough food in them. And then the next slide. That's our third diversion point, and this just before the research well. And again, this is in case we do not meet our specifications in regards of water performance. You can go to the next one. Of course, to be able to have an automated system, we have to have a lot of different analyzers. And maintaining these analyzers is critical, very, very critical. And we have a bunch of them before and after each process, again, trying to understand what is happening with the water as move and advance in the treatment process. So we always need to make sure that we have a representative sample. Sometimes, you know, the analyzer is way or is in have a long distance from the main process, and that's a problem. You need to make sure that you always have a representative sample, and always, you know, and verify and calibrate analyzer as needed. At the beginning, I mean, this is very new to us, or was very new to us, so we didn't really know how reliable were the analyzers. So at the beginning, we were doing everything like daily, and then as we were collecting data, we start like to relax on some of them. So some of them we do like daily checks, weekly checks, and some of them even monthly checks. So again, it's depending on how reliable is your analyzer. You can go to the next one. Okay, so this is the main critical control page that we have for different reasons. Just to give you an example right away. So the first one, so it says influent pump station conductivity. So we correlate conductivity with bromide concentration, and that's to make sure that we do not form too much bromide. So we have an alert value of 1400 microsiemens per centimeter. If this value gets close to that, to 1400, it's going to start alerting the operator. But if this value goes higher than 1600 for more than 10 minutes, it's going to put all biofilters in filter to waste. And then the water is not going to be processed anymore. And the reason is, in this case, I put here bromide. And then we have different actions and different time delay for different control points, just to make sure the water is safe. So I'm going to be talking more about how we achieve this one specifically. So you can go to the next one. Okay, so for bromide, we have like five different critical control points, and this is one MCL that we struggle, or we used to struggle a lot, and now everything is under control, which is good. But like I mentioned before, we correlate bromide. We correlate bromide with conductivity, and if conductivity is high, that means that bromide is also high, and we can potentially form bromide during the ozonation process. So here on the graph, you can see like if the conductivity is higher than 1600, that's a potential for us to form bromide right here. And of course, depends on how much ozone you're dosing and that, but this is just for us as a limit, as a safety factor here, just to make sure that we do not produce any bromide. Like I mentioned before, we use monochloramine to control bromide formation. And here on the graph on your right, you can see, for example, if we do not use any monochloramine, we dose anything like this. This is the blue points right here. At a dose, apply ozone dose of 14 milligrams per liter, we can form up to 30 micrograms per liter of bromide, which is 3 times higher than the MCL. But if we use 3 milligrams per liter with the same apply ozone dose, the bromide it gets better and it's under control and way below the MCL. So right now we have a critical control point that if for any reason the ozone demand is higher than 14 milligrams per liter, and you can see it right here on the ozone dose right here on this table. If for any reason the applied dose is higher than 14 milligrams per liter, then we're not going to process the water all the way, and it's going to put the biofilters in filter to waste. And again, this is just to make sure that the bromide doesn't go all the way to the aquifer. That's the main goal. You can go to the next one. Okay, so for LRVs, we have different ones. And again, our goal is to achieve the 12-10-10 rule, like Uwe mentioned before. So we need to achieve log removal values for viruses, which is 12, and then 10 for crypto and giardia. You can go to the next one, because I'm going to talk to a specific one. So for example, for Fluxset works together with biofiltration, and this is based on the Surface Water Treatment Rule Guidance Manual from 1991, and you can go to the specific section 5.5.2. You can get up to 2 log removal values for viruses and 2.5 log removal for giardia if you keep the turbidity less than 0.3 NTU, so you can get those credits. And then you can get, you can also get 3 log removal for crypto if you also keep the turbidity less than 0.3 NTU. But if you want to get extra credit, and you want to get an additional 0.5 log credit for crypto, you need to make sure that all the individual filter effluents are less than 0.15, and that's specifically for each biofilter. So that's why we have the CCP as I'm highlighting here. Like individual filter effluent has to be less than 0.15, and if not, it's going to put biofilter and filter to waste, or it's going to call for a backwash. So just based on these, I guess, rules, we can achieve like 2 LRVs for viruses, for crypto, and 2.5 for Giardia. You can go to the next one. For ozonation, we can also get some credits. This is based on the long-term 2 enhanced surface water treatment rule toolbox guidance manual. This is also based on drinking water standards. The way that we operate our ozone system is based on LRVs. So this is our main set point. So we need to make sure that we are always higher than 3, and that's to be able to meet the 12-10-10 across the whole process. So of course, if the ozone feed fail, that's very bad, and it's going to bypass the biofilters. If the ozone LRV is approaching to 3.3, so our set point is 4.5, just to be always very conservative. But if it is approaching like 3.3, just because the ozone demand is super high, it's going to again start alerting the operator first, and then it's going to take action if it drops less than 3.3 for more than 5 seconds. So this is like super quick. So again, this is based on some guidance that you can find in the long-term 2 enhanced surface water treatment rule toolbox, and it's based on CTs, it's based on temperatures, it's based on flow. So we're monitoring that very closely in our system. You can go to the next one. Okay, so for UV, like similar to what Uwe was mentioning earlier, it is also based on equations. When we request to have a UV system here, it was designed to achieve 4 LRV for viruses specifically. And to be able to do that, we need to meet a design dose of 186 millijoules per square centimeter. So as long as the dose is higher than 186, we can make sure that we're always getting like 4 LRV for viruses. And we can get also 6 for crypto and 6 for Giardia. So of course, the critical control point here is like, if for any reason, and this is just to be conservative, if for any reason the UV dose drops below 195 for more than 5 seconds, we're going to divert Swift, and then we're going to be able to put the water into the ground. So again, this is just based on CT again, and based on flow and everything else. You can go to the next one. All right, so if you were paying attention and if you are good in math, you will notice that I was lying to you and I'm not achieving the 12-10-10 as I was promising. So we're achieving actually 9-10-10. So for tasting specifically, and you can just click for the next one, Uwe. For tasting, if we want to achieve a tasting, if you want to give people the opportunity to taste the water when we do tours in here, we have a separate system that we can achieve 4 LRVs for viruses just using chlorine. And that's the way that we achieve the 12-10-10 rule above ground. And I'm mentioning above ground because we can also get credits once we put the water into the ground. And you can go to the next slide, Uwe. Thank you. So we can get credits by SAT. SAT is soil aquifer treatment. So once we put the water into the ground, the water is going to still be treated naturally. And based on California rules, for 1 log, we can get up to 1 log for 1 month of travel time. And we can get up to 6 log removal reductions. So basically 6 months of travel time. So for full-scale operations, we're going to be relying on SAT to be able to achieve the 12-10-10 rule, and that's been granted to us. So ozonation for full scale, we're not going to be using monochloramine, but we're going to be using hydrogen peroxide, which is better for oxidation of specific contaminants, but we won't be able to measure any ozone residual, so we won't be able to achieve any disinfection credits or achieve any LRVs. So that's the the bad thing about that. You don't in the current guidelines for drinking water, we're not able to get any LRV credits if you don't have any ozone residual. So, which is not a problem for us because, again, we can rely on SAT to be able to achieve the 12-10-10 rule. And we know still, even if we don't have an ozone residual, we know that we can still remove some viruses. So and that's what we're trying to, I guess, to change here, like change the rule for LRB credits here in the United States. And that's something that we're working, right now. You can go to the next one, Uwe. All right, so I mentioned the TOC, we have to be less than 4. And by doing that, we're also controlling a lot of different contaminants of emerging concerns. What I'm putting here is a barcode that you can scan here, and you can actually see all of our quarterly reports. Those are open to the public, and you can see all the data that we have since May 2018. And every quarter we have been providing this data, and you can see everything that we are. This is just a snapshot, by the way. This is not everything, but you can see the average. You can see the minimum report level for everything that we're doing, like different microorganisms, like disinfection byproducts. You can click on the next one, Uwe, because I'm just showing like different like tables, like inorganic chemicals, organic chemicals, and you can see basically everything and how that correlates with the TOC of 4 milliliters per liter. So if you're thinking about anything that are you measuring for PFAS or for anything else, yes, we are, and all the data is right here, and you can see again how this correlate with TOC. And of course, TOC here is going to vary because the way that we operate is that so we have 2 GAC vessels, and when the TOC is approaching to 4, that's when we replace the GAC. So sometimes you will see in these reports that the TOC is very low, and that means that the GAC was just replaced. And when the TOC is high, that means that it's getting close for replacement. So just keep that in mind if you start looking at this data. You can keep going, Uwe. And then we have more data. You can go one more. And then this is just a summary of our main treatment process. Basically there is a lot that we're receiving in our collection system. Like there is a lot of bromide, PFAS, 1,4-dioxane, total organics, pathogens, nutrients, and contaminants of emerging concerns. The wastewater side mainly focus on removing nutrients like nitrogen and phosphorus. The TOC coming in to SWIFT is about 10 to 12 milliliters per liter. And then, and then I'm not going to explain this because of time, but you can see exactly what is happening on each specific process. So yes, I guess one thing that I want to highlight here is that for full scale operations, we're going to implement ion exchange, and this is specifically to remove PFAS, so PFOA. So right now, GAC is our main barrier for PFAS, but we don't want to rely on GAC to remove PFAS specifically, because that's going to basically decrease the bed volumes or how much time we can run it. So just to give you an example, if we focus on TOC, GAC can run up to 40,000 bed volumes. But if we focus on PFOA specifically, we can only run up to 20,000 bed volumes. So right now we're replacing the carbon more often just to be able with that PFOA. But for the future, we're planning on implement ion exchange. So we can, again, GAC can focus on TOC, ion exchange can focus on PFOA, and then, everybody's happy. And then we have, once the water is into the ground, we have monitoring wells. We have the first monitoring well, which is only like 50 feet apart, and the water takes about 3 to 7 days just to travel that time, and then 8 to 8 months to achieve 500 feet. So we can stop here. I know that you might have some questions, so we can jump into those, but thank you.
Thank you again, Uwe and Hermano, for your time and sharing those really interesting insights. That was really something, and the detail behind that was fantastic. So thank you, really good. Today's sessions really highlighted both the opportunities and the complexities around advanced treatments and potable reuse, particularly indirect potable reuse. As the industry looks to improve resilience, sustainability, and long-term water scarcity, I think it's really important we start addressing these and sharing these lessons, from around the world. So, hopefully today was a really good start in that process from Xylem. So thank you. We're not quite finished, so the exciting part, we get to ask some questions from our experts and guests today. But before we do that, I'd like to just jump into the next poll. So if we could bring that up quickly, and your participation would be really, really well appreciated. Thank you. Okay, would you like us to follow up with your discussion on an IPR project? So if you could just answer those 3 points, and then we'll move on to some questions. Thank you. Just give that a couple of minutes, well, another 20 seconds or so, just while we get those responses up. Slowly coming through. Excellent. Okay, we'll leave that there. So yeah, again, appreciate the feedback. This is really interesting for us to go away and look at these sort of events and gauge the interest going forward. So thank you. Okay, so now we'll jump into a little bit of Q&A for Uwe and Hermano. Hopefully throughout the hour or so, you've been putting your questions into the Q&A box. Just a brief reminder, if you do have any questions, please put those in so we can get our experts to answer those. So I think in no particular order, if it's okay, I'll start off with sort of an opening technical question here that has come through on the chat. So what are the requirements or the expenses for service and maintenance of online instrumentation? Obviously, it's this process and these advanced treatment processes are critical to these pieces of equipment. So can you give any insight to that? Let's go with Hermano from an operational perspective.
You're talking about price?
Yeah, operational servicing, pricing.
Yeah,
the cost of.
Yeah, no, that's a really good question. I cannot give you numbers right now. I mean, I could give you numbers, but I haven't done the math. But what I want to say here is that we're not trying to spend more money of what we already plan to spend. So basically, what we're doing is like, instead of, making upgrades on the wastewater utilities to be able to meet permit, we're going all the way to implement SWIFT to meet drinking water standards. So of course, we're going to be spending more money now, just trying to put all these facilities together. But in the long term, basically, we're just spending the same money. So basically, the ratepayers are not going to see an increase on the water bill because, again, we're not doing anything that we wouldn't do in the future. So I just want to put that perspective in there for you guys.
Brilliant. Thank you, Hermano. That's really good. Okay, a question from Oliver. What is the approximate cost or treatment cost per cubic meter for the whole process? That's a difficult one.
It depends. So it depends for us, but the most expensive part for us is GAC. So it's, I should say, with how often you want to or you need to reactivate the carbon. So again, for example, if we focus on PFOA, the GAC is going to lose like in a shorter time. But if we focus on TOC, we can maximize the TOC capacity and we can absorb more or better. So that's what we're working on. Even though we're implementing ion exchange after GAC, in a long term, it's cheaper to have ion exchange to focus on PFOA and GAC only for a longer time. So yeah. I don't know, Uwe, you have anything to add on that?
No, to be honest, I don't know the cost of this entire treatment train very well. But maybe one thing to note is I think it depends a lot on the scale as well. So also when you talked about the monitoring before, so if you have a smaller scale system, the maintenance and the instrumentation will be much more relevant compared to larger systems.
Okay. Yeah, excellent. Appreciate that. Thank you. Okay, another one from Vicky. Can you elaborate how membrane and RO systems need to be monitored in potable reuse systems? Maybe Uwe, one for you.
Yeah, I can start with that, even though I'm really not an expert on membranes. So regarding RO, there are different concepts, and they're discussing more and more right now. So initially they're mostly using the conductivity to really make sure that that RO membranes are working well. As I mentioned, that gives you a lower disinfection credit, because with the conductivity you cannot really indicate a log removal, so it's not very well correlating to the performance of the RO, or if it's not performing that well. So that's the driver. Now they're using different surrogates and testing, and the current discussions, I think, went from sulfate to the most recent one is strontium, to measure strontium in the inlet and outlet, to show the removal of strontium, because that apparently correlates very well with the viruses, up to, and I think they're discussing up to like 3 to 3.5 log for this right now. So that would be continuous monitoring of strontium. Then of course you need to increase the costs of the instrumentation and the effort, but you would gain more credits for the RO membranes.
Okay, thank you. Amanda, anything to add, or are you happy with that?
Yeah, I'm not familiar with membranes. I've been doing the carbon-based technology for years, so yeah.
Not a problem, not a problem. Okay, so we've got a couple of minutes left. I'll see if we can squeeze in the last two questions from Katerina. How is the bromide and conductivity correlation being achieved?
Yeah, so no, that's a good question. So so when we started with the pilot, which was just a small system, we were in a different location. We didn't have any issues with bromide, or at least not too many issues. So we had it like dialed in. But then we moved to a different location, and we thought that we could just use the same parameters with ozone dose and everything. But then we realized that sometimes bromide was higher in some days, meaning that bromide was higher on the MCL. We were like wondering like what is happening here, right? So we were able to actually do some source control and actually understand better what was coming into the plant. So we correlate bromide with actually a landfill leachate facility that they can discharge like 50,000 gallons per day. And they were doing that in a period of 6 hours. So during that period, bromide was super high, bromide was higher. And then we needed to do something about it. So we asked them if they can discharge to us like 24/7, and they said we would love to do it, but they don't have a VFD to do it. So we bought that for them, and now they can discharge like 24/7. But going back to your question, it's based on data, right? So we have a lot of data. We collect daily bromide, and we also have conductivity monitoring, so we can create a correlation based on that data. So we know that when conductivity is like 1600, probably bromide is like 0.5 milliliters per liter, which is high. And that's a problem for the ozone system. So again, you can create, or you can correlate your data based on data that you are collecting, and it will be different depending on where you are located as well. So that's something that we learned too. But that's a really good question.
Yeah, maybe to add to this, this will most likely be very, very site and case specific correlation, because you're using here the conductivity as indicator for bromide levels in the water. And of course we have different sources for bromide that in wastewater where elevated bromide levels may come from. So that's probably different at different sites, and you would need data for other sites as well.
Definitely.
Fantastic. No, that's great. Appreciate it. Okay, a few more minutes, so we'll see if we can give a quick response on this, and then I think I'd like to just ask a macro question, because I'd really appreciate your opinion on this. So before we get into that final question, again from Katerina, how is MDMA controlled?
That's a good question too. So so MDMA is a byproduct coming from right after ozonation. Biofiltration can remove MDMA, no problem. So that's our goal. So after biofiltration, it should be non-detect. But of course, it can't just happen right away. You need to make sure that the biofiltration is acclimated. So for us, it took about 2 to 3 months for the biofilters to acclimate. And we can see that during that acclimation period, full nitrification happens in the biofilters. Manganese is well removed, iron is well removed, and if you can prove all of that, MDMA is also well removed. And we have data that I can show you if you wanted the data. But yeah, usually MDMA is well removed right after biofiltration.
Perfect. Anything else to add, Uwe?
No, that I think for this carbon-based treatment that's quite clear. So in RO-based treatment, NDMA removal is achieved basically by the final UV AUP. So what they do is they monitor the NDMA concentration in their feed water, and then they model how much would be removed in the membranes, so that they have a final concentration going into the UV AUP. And this will be the design for the UV AUP. So how much does this need to remove? And NDMA is basically removed by photolysis. So it's not the radicals, it's really the UV irradiation responsible for NDMA removal.
Brilliant. Thank you. Okay, and I think just to finish on a slightly more macro level, be really interested in your perspectives. So we'll start with Uwe. So in your view, what do you believe is the greatest barrier affecting the adoption of reuse globally? Is it public perception, regulatory complexity, affordability, or operational capability? I mean, what factor you think is the biggest barrier we need to overcome?
Well, that's a tricky one, and I think it's different in every region of the world. So when looking here from a German perspective, I would probably see it's still a regulatory question. Mm-hmm. So we're just for the EU, we're just going into non-potable reuse. That's a big step for Europe already, and the potable reuse is not in discussion very well. So I think here this is even more. Elsewhere, I would assume also costs is often a driver. So at the end, you need to check what is the more economical solution, and as long as resources are available, then the treatment of those is probably in many cases cheaper. But if there is a really severe demand, and we see this in many places of the world, like in Namibia and Windhoek, they installed this in the 60s, 70s, direct potable reuse, because they simply have the demand. And Barcelona, Spain, we've seen the severe drought recently. So then they immediately started linking also into potable reuse options, indirect potable reuse in that case. So then it's probably a mix of economic drivers and also public perception that's of course increasing when they see the demand, and when they see the reservoir is empty, basically.
Perfect. Hermano, anything to add before we wrap up today?
Yeah, no, just to agree with Uwe. Yeah, it's basically based on the cost, economics, but also politics. I think that sometimes politics, it can influence, how different cities, implement water reuse. So yeah, just keep that in mind too. But yeah.
Fantastic. Mm-hmm. Brilliant. Well, thank you both for your insights today. We really appreciate it. And again, thank you everyone for joining us. This session has been recorded and it will be sent out. Thanks a lot and good afternoon.
Thank you.
Thank you.